Okay, now I know it's been a week or two since we met last, I don't know. So I wanted to just do kind of a decent review. We're going to do this Maxwell-Boltzmann today and Friday, extra lecture Friday on Maxwell-Boltzmann. And as I promised, I'll try to very much try to keep that relevant to the homeworks, a lot more than I did last time. I hopefully didn't completely bomb that last semester, but anyway. Okay, so review Maxwell-Boltzmann, and I'll give you an example of a test question that I almost inevitably ask. So remember that one of the, I never like to throw things at you without a derivation or some substantial explanation, but I violated that with the Boltzmann equation, which is the probability density of how nature doles out energy. So you grab a gas molecule and you ask how much energy it has. The probability of your observation is dictated by this thing here. It is derivable. It's based on the laws of conservation of mass and energy, which I'm pretty sure those are true. It's a 2 or 3 page derivation. You do know enough to do it, but I'm just not. Okay, so then we plug in 1/2 mv squared. Not terribly difficult from there. We had a little problem with the denominator. Well, not really a problem with the denominator. We did the denominator first. Remember that is a normalization. That's the thing that normalizes the probability that makes the integral over all possibilities 1.0. Remember that we can put that in words. The probability, let's do velocity, the probability that something is moving or is not moving is 1.0. This is the part that makes that happen. This is what that looks like after we do. And again, this is all done in class and in the little write-up I gave you. And I'm going to forget KB a lot, so I'm just going to roll with that. So hopefully, I'm sorry about that. Well, I'll tell you what, how about I just try not to do it? KB. I've noticed the video, I noticed that the audio, maybe it's just my ears are getting old, but I noticed I had trouble hearing myself unless I'm facing the camera, so I'll be careful about that. Okay, so anyway, that's the normalizer. Then we have the business end, and there's not really much to say about that. It just is, it is what it is, so there it is. The next thing we had is a geometry factor. We had to go from XYZ. We live in an XYZ world, but it's really hard to do things like calculate average velocities with XYZ. That's because velocity is the square root of x squared plus y squared plus z squared. You run into integrating in x with a term that has a square root with an x and a y and a z in it. Anyway, there's a technical problem with doing that that's really hard to solve. So what we really like to do is net velocity, and to turn the partials, let me do an aside here. And this was the subject of last lecture, and I did put the video, I was able to mesh the figures, the PowerPoint figures into the video. I found it a little awkward looking, but probably better than not doing it. Anyway, so last video, last lecture, and look at the video, I did a little PowerPoint showing how you convert partials into partials in x, y, and z into the net partial. Okay, so this is like a geometry factor. That's how often I put that. So that's like a geometry factor. And again, there's 2 ways to think about the net, the partial of the net. And one is that it's because of what I just said. You want to use this thing as a function of net velocity because that makes a lot more sense to us. You also have net velocity in the exponential. So you have to integrate on that. You have to. Remember when we were doing some of the early last semester when we were integrating work and that's minus PDV. You had to be careful whether volume was it hiding inside the pressure. You can't let, if you're going to integrate on something, it can't be hidden somewhere else in the integral. You have to know that it's there or you're making a mistake. So that's another reason why we need to have that net velocity because it's right there as well. So again, let me remind you, this normalizes it. That's just kind of the business end. This is basically a geometry factor so that we can express this as the net. So again, I promised you on the test I might throw this or a similar equation and say, hey, just tell me why, why is this there? And then you just say what I said. Don't want you parodying stuff, but anyway. Okay, now the properties are, I'm going to call this MB, Maxwell-Boltzmann. One of the things to look out for is I will often on exams and the homework, this next homework, the hard part is just setting it up correctly, recognizing what it is for what it is, using it correctly, because remember, I give you calc identities on homeworks and exams. Now, in that little write-up I gave you, I did do the bloody, awful integration by parts to show you how to do integrals with this longhand, but I don't require you to do that in class. And again, that's internet for you, right? You can look up calc identities in 5 seconds, so I'll just go ahead and give them to you. But just to let you know, so I couldn't do that when I was your age. So we had to do all the calc by hand. But we got simpler questions. I give you calc identities, but I give you harder questions. So that's how I balance that out. Anyway, okay, so Maxwell-Boltzmann velocity. So again, the setup is, show that it's normalized, right? You had a question like that on this present homework. Okay, the trick is, all right, I've given you that, so you're not going to screw that up. That's what will get you. And then identifying the correct calc identity, and you should get 1.0. Okay, fine. Easy points. That would be an early question in the exam because it's obviously easy. Okay, other bits. And this is towards the end of the lecture Friday. That was going a little too fast, and some of you were even asking me some days later. So I knew I needed to slow down and back up, and so that's why I'm reviewing this now. Okay, the way you calculate an average is number one way to lose points is to do this. Is to do that. What did you forget? V. Right. You forgot to take the thing that you're taking the average of. How do you, all right, for one, you just forgot. You do it and you get 1.0. Did you do it wrong? Yeah. Right, because I just said you did it wrong. And how could you know other than you just know not to do that? You got what? The probability. You got 1 point, right. What's the odds that on an average velocity? For one, you're going to get exactly 1.0, and number two, you're missing units. If you do this right, you're not going to be missing units. So you've got two ways of knowing whether you have screwed up and done an average value calculation with a probability mathematics, because you get a probability answer. Something unitless and something that's either a half or one. Then you've screwed up because I didn't ask for probability, I asked for average. The other thing is limits. Now, net velocities, nets cannot be zero, cannot be negative, right? And remember, if you get confused with that, look at the cheat sheet on the exam where I'm going to remind you that, here's an aside, that net velocity is the square root of some term squared, and now you should know that that can't be, and again, I never write these the same way twice. It's some weird psychological problem, I guess. But anyway, so you should know that the proper limits are 0. Be careful if I do this with x, like on your homework. If I do it directional, then you can be negative because things can move backward. That's the meaning of that. Okay, now, again, on the handout, the chapter that I wrote for you folks, hopefully that book will actually be released to the world of the internet in the next summer. That's the plan. But I need to write it at some point, so now is as good a time as ever. I show you very longhand how to do this. I also show you how to do it with a calc identity, which is what I think I did in class. You also end up, no matter which way you do it, you end up with a mess of, and it drives me crazy too. M to the 3/2 over a constant squared to the 3/2. The constant has m in a pi, and blah, 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 blah. It goes on forever. It is just a mess of So I'm just trying to, I've done this so many times I remember. Anyway, so there you go. So work through all the mess of the constants, however, longhand, identity, whatever, there you go. And the other thing is also if I want to throw a calculator question like I did on the homework and maybe on the exam, that would be me giving you points. Just remember that M's are single molecules. That would be, look at the periodic table, divide it by 1,000 because masses are in kilograms and standard SI, which is weird, I never quite got that, but standard masses are in kilograms, divide by Avogadro's number. Now some of you on the homework were getting confused on number 6, where the trick was I was giving you information not for the mass, but for the temperature. So anyway, just look out for that. That's a good example of a test question because it's relatively straightforward, but oddly was a little tricky. Okay, so this is, I'm still reviewing. Now let's get into some new material, which is average. I call this, the correct word is a moment. This is a higher moment.
Hey, Professor.
Your question?
Before we go on to something else, can you just explain what the VRMS is? Like what it actually means?
Well, yes, I'm doing that now. Good timing. Great. Okay, so the correct mathematical term is that these are higher moments, and like a lot of things, I just find that we tend to give words to things, and then you think that there's some esoteric, difficult new concept that you're having to learn from scratch, when the reality is it's just the average of the square. Now note that this is not the same as the average squared. And I showed you last lecture, I just threw up some numbers like 3, 7, and 9, and I showed you that the average of those numbers, and if you square it, is not the same as if you square them all and take the average. That's just this mathematical reality that, and I don't quite, I mean, I can certainly do that calculation. I did it on Friday, and it works, and I can accept that, but it just is what it is. Now, Right. So this is a thing you can do with Maxwell-Boltzmann. So let me go ahead and do it. And I'm going to do it in a very hand-wavy way. The thing I sent you does it longhand with integration by parts. You actually have to use integration by parts twice. It takes about half the class, so I'm just not going to do it because you can also do it with an identity. I'm going to do it with an identity, again, just for practice. And there's more to it. So I'm just going to do this, but then I'm going to show you something cool that comes out of it. Now, note that, I mean, I can calculate the average of it. I can calculate the average of the third moment, which is the cube. I mean, we can just do this all day long. It's just why. Why would you? I get average velocity because that's immediately sensible to me. But why am I doing the square? Let's just do it. Look at the result, and then I'll show you. And I'll show you what it's good for. And let's see, where am I at now? Again, I want to. I have another little, so get the limits right. This is a net velocity. The lower limit's 0. The upper limit's always going to be infinity, no matter what I ask. Okay, I've got a 4 pi b squared. That's the geometry. I'm asking for the average of the square, so I multiply it by the square. So I'm looking for an identity with a quartic, with the x to the 4. And I see that, again, I'm kind of screwing up because I normally, you see, sometimes I just don't put these the same way every time just because my head is a bag of cats. Okay, here's the normalization. My handwriting isn't so good, and there we go. I hope that's right. Is that right? I think it's right. Again, remember, a lot of this pain is all just a mess of constants. Really, it's e to the minus ax squared. It actually is x to the 4th e to the minus ax squared. Can you hack that? Can you turn the page to the integral identity and look at the answer? Can you do that? Are you smart as a 4th grader? So, and to make it less scary, always try to take out the mess of constants. Just get rid of them. I often call them the letter Q, and then I just forget about them. And we're left with, again, something that's relatively simple. And I also mentioned to you, I stupidly have the wrong identity in the little book chapter I sent you, and I fixed it, and I'll upload that. It's not a big deal. Okay, so hopefully I've asked this question, you've set it up correctly, you're not freaked out by all these constants. That is just not that bad, really. I mean, it's just not that bad, especially because I've given you this. I've given you this. And as usual, this is what you find on the internet. And so I'm going to give it to you. You just have to use it correctly. Not that hard, not that hard. And also remember that you identify what's what, just plug it all in and just leave it alone and get full credit. I will, of course, simplify it because I kind of need to. So what I end up with is a mess of constants, which is unfortunate and oddly painful, despite the fact we learned algebra in the 6th grade. Okay, now I've got a 3 pi to the half. Now I've got a 8. Okay, trick is to identify what A is. A is, of course, m over 2 kt. I've asked you this before. Let me do it again. Is there a minus? Is it m over 2 kt or is it minus? No minus, right. See, it's there. It's already incorporated. So I harp on that because I see that's how to make mistakes. So what I end up with is, look at this. This is something you learned to do in the 6th grade, yet when you pump it full of steroids, like, oh my God, like I've done right here, it is very unfortunate. Especially because it does simplify to something that's very simple. There you go. And seriously, this really, here, I don't want you to get confused between, there you go. It's just that easy, 3 kt over m. Okay, so let me leave this up here, and then let me, so I've done something because I can do it, right? And cool, but is there something else? Is there something more to it? And let me first do some plotting while this is, I'm going to tell you what, no, I'll wait. Let me, sorry, I got too much going on in my own head. I'm still trying to learn to count from 1 to 10 in Chinese as well. Let's see, what can I do with that? Let's see. Okay, average v squared is 3 kt over m. Sorry, I've already done it a zillion times. I keep forgetting the kb. All right. Okay, so what? Now, the reason this is special is I've got kt and not square root of kt like I did with average velocity. Here, it's not squared. The reason that's important is, let me remind you that I can certainly do some algebra. This will be a little bit easier. Okay. So I multiplied by Avogadro's number. Now the reason I did that is hopefully you remember that Boltzmann's constant times Avogadro's number is 8.314 joules per k mole. That thing you've been learning about in high school chemistry in the perfect gas law. And now I've got mass in kilograms times the number of moles, so that's the molar mass, but it's in kilograms, so just be careful. So I'm just going to call that big M. Okay, so what? Now notice that that's the mass in kilograms for a mole. So I'm describing a mole. So let me remind you, for 1 mole, PV is equal to RT. N is 1. PV equals nRT, but N is 1. Okay, now I've got 3 PV over M is equal to the average of the square velocity, and therefore the pressure is M average V squared over 3 right. MV squared over, yeah, is that right? I feel like, yeah, that's right. There you go. Okay. Okay, can you measure a pressure? Could you look inside, pressure of a balloon? Can you look inside of it and tell me how fast the gas molecules are moving? No? Can you now? Huh? Kind of cool, right? You can measure the pressure of a balloon, and now you can know how fast the individual molecules are moving inside that balloon. And that is what PChem is all about. To take something that we're really doing, and pressure is something that I'm sure cavemen kind of understand. They just didn't have measurements or units for it. 1800s, we had abilities to do that. Seriously, 1800s, we started using inches of water for pressure. We've been able to do this for a long time. Now, before they even knew molecules existed, now you can back out the velocity of a molecule inside that balloon because we can do stuff like this. So again, one of the ultimate goals of all of physical chemistry is to do something exactly like this. So, yeah. It's on the final. Anyways. So there you go. Is there any question?
Yeah, this is measuring the pressure and finding how fast the molecules are moving. That's only for ideal cases, right?
For what?
For ideal cases.
Ideal cases, ideal, perfect gas technically, that's the technical correct word. And you weren't in last semester, so I can tell you that last semester we did a couple of examples where it turns out that perfect gas law works extraordinarily well for gases near room temperature and pressure. Like the air is like a tenth of a hundredth of a percent. It's incredibly small. You only see crazy deviation when you're at extremely high temperature just because it's extreme, or when you're extremely low temperature when the gas is about to liquefy. Because the perfect gas law isn't going to describe a liquid. So that's when you see deviation. So for the most part, this is actually pretty cool. And next Friday, I'm actually going to show you another good reason why I'm going to show you next Friday why the perfect gas law works as well as it does, again with Maxwell-Boltzmann stuff. So, yeah, okay. Alrighty, last bit, let me graph this stuff. Well, I hope you thought that was kind of neat, right? But anyway. Okay, so now I want to graph this stuff. I won't necessarily put down numbers, although you know that these are on the order of, hundreds of meters per second. And the average velocity is that here?
No.
Some of you looked at what I said, some of you didn't. It is not here. Average velocity is slightly off to the right. That's because this is not a bell-shaped curve. And this is also why you need to do all these probability type of mathematics. You get some really counterintuitive stuff happening. I would normally have said, well, the average must be here at the top. That is true for bell-shaped curves. This is not a bell-shaped curve. It's almost a bell curve, but it's skewed, and that means the average is not at the top. Now, RMS, which is the square root of this, tends to be slightly to the right. Now, this is exaggerated, and remember, I'm going to call them both. So it's the square root of the square, or RMS. Those are the same thing. I'll put one or the other kind of randomly. Again, this is a bit exaggerated. It is a little bit off to the right. And there you go. Now, this thing, it is still, to a person, it seems like this point is important. And it is because it's the top. And so we often will try to do some calculus on that thing. This thing, the top probability, is called most probable. So let me do that here. It's actually pretty easy. Now notice that I am not using the average deal, because the calculus I do is completely different. So it doesn't get to pick up that little sandwich of a greater than, less than sign. I never quite got where. I'm curious where that symbology comes from, but anyway. So it doesn't get its little symbology, it's just called most probable. And again, I don't know that it's really meaningful other than it's just at the top of the peak, but the averages are always a little bit off to the right because again, these are not bell-shaped curves. Now I'm going to show you a couple of other examples of probability distributions that are not bell-shaped that are kind of important towards the end. Okay, now how do you do this? How do you do this? This is easy. If I ask this on the exam, and I think I have you do one on the next homework, thank me, because this is the easiest one. This is actually, I should probably start with this one, in all honesty. All right, so this is the derivative, Maxwell-Boltzmann with respect to velocity. Okay. Now, I try to be very careful with my calc and use the right symbols at the right time for the right place. A derivative is a derivative. And we can certainly calculate the derivative. It's rather easy. I hate a little bit of e to the x. I hate derivatives of e to the x. That's actually easy. The derivative of e to the x is e to the x. The derivative of e to the x squared, okay, it gets a little harder, all right? So anyway, whatever, we can do this. Now here's the trick though. We set it equal to 0 because the calc, now hopefully you do remember this, right? The calc definition of extrema, of maximum and minimum, is when the damn thing is flat, that means the derivative is 0. The derivative is 0. So there you go. Now here's the thing. You notice I've written this kind of funny? It's because when you set it equal to 0, not any velocity is going to solve that equation. So before I add the 0, I wrote it like this, but when I set it equal to 0, then I have to understand that that velocity is not velocity, it's a very specific value. So, to do this, let me put all the constants as a q. I've got v squared e to the minus mv squared over 2kt equal to 0. Now I need to be putting most probable into the v's as soon as I set it equal to 0, but let me just keep going. In case you've, if you look at this and you're a little bit calc challenged, this is the highest level of calc I'm going to ask you to do in this class, but you do need to do it. If you're having trouble, I told you a zillion times, please come see me. So I've got two terms with velocity, so you're going to take the derivative of one and leave the other one alone. Leave the other one alone. I hope if I would do it right. I'm still not writing mp on the velocity, so I'm already screwing up what I told you to do. Okay, and then you do the opposite. Then you leave the other guy alone, and you do the derivative of the other guy. And as I mentioned, derivative of e to the x is easy, but as soon as it's e to the function of x, it gets a little harder. So anyway, that's the derivative of the argument. I've also taken care of the minus sign here.
I think you're missing a term.
Okay, hold on a second. So, and I set that equal to 0. Am I?
The mass, the m, in between the parentheses.
2mv, right? I got it? Yeah. Okay. I'm not going to spend any more time on this because it's really just a matter of algebra. You end up with this. 2kt over m. Which is obviously less than the square root of 3kt over m, and pi, if you recall, this is 8 over pi, which is between 2 and 3. So it all makes sense. Anyway, on an exam, I'll give you the distribution of cats. You find the most probable cats. Do this. It's really not that hard. I think you actually have a little bit harder time with the calc, the integrals, than this one. But it actually is slightly, I find that, folks, if you know what to do with most probable, and I just showed you that, just remember that, the derivative, you're better with derivatives. I would argue that if you can just kind of tone down the anxiety during exams, you realize the integrals are actually easier because you're not actually doing them. because I give you integral identities. Okay, last bit, and we'll end with that, is relative velocities. And then we'll spend Friday on applications and the extra hour doing, I've thrown some fairly not difficult calculus questions on problem set 2, but nuanced ones about transformation of variables and Jacobians, so we'll spend a lot of time on that on Friday, extra hour. But relative velocity. Okay, velocities with Maxwell-Boltzmann, we've beaten them to death. There's really nothing else I could possibly ask of this. So on the exam, I told you I'm going to be asking about the average number of something else, and I'm going to go with cats or dogs or something. The point of that is, do you know that probability densities integrate to 1? Do you know that you need to multiply by the thing you want the average of? Can you get the limits right? Can you use a calc identity? Those are reasonable questions. And we're done. Okay, relative velocity, this is kind of cool. I don't know who thought to ask this, but get this. I've got a vacuum chamber. And if you've ever seen pictures of these things, we have a couple of groups who do research in vacuum chambers. They have little portals, and it swear to God, it looks like this stuff looks like it could be inside of a submarine. Little portals, you can look inside of it, and imagine that I am sitting with a stopwatch and timing molecules. I would calculate average velocity like you just saw it. Square if I could do that. Now, instead, get a saddle and write a molecule inside the chamber, right? Write a molecule inside the chamber and do the same thing. Get your stopwatch and make observations. So again, the point is that I'm now inside the chamber, writing a molecule. I used to ride horses, it's a long time ago. And I'm going to make the same like observation stopwatch and write down numbers and average velocity, but now I'm inside the chamber. Would I get the same velocity? No. Well, of course, because I'm doing this. Now here's my problem with this. Obviously, I'm not going to make the same observation. My frame of reference matters. If I'm driving on the street, and this will happen too, and I have like a laser gun, I will not calculate the same average velocity if I make the same observation on the side of the street. And that's bizarre because now part of me thinks that, of course, when I think I can draw okay, you guys can tell me. Part of me says that makes sense because you know that if two vehicles are coming at each other, the velocity is like massively magnified, right? You know that energy is velocity squared. So when you hit head on, it's really bad. But counter to that is if we're going in the same direction, even if we're going the speed of light, we're not moving at all relative to each other. So I never quite got this. Again, relative velocity, if I calculate the average velocity while I'm a participant, while I'm inside the chamber, I will not get the same value as if I'm outside. I get if they're coming at each other, they seem to be moving twice as fast, but counter to that is if they're moving in the same direction, they're not moving at all. It would seem to me that these would cancel each other out, but they don't, and that's what we're going to show. Anyway, that's the point. And we're going to do, there's something cool you can get out of this too. Hopefully I'll get to that, but I want to show you how you do it. Okay, relative velocity, just like I just drew with the cars, what you need to do is you need to have vector A and vector B, and I didn't do this in the little write-up I gave you, but vectors have little hats. The relative velocity, VA minus VB, oh my God, how do you do that? Or is it B minus A? I think you get this. This is the relative, and this is VA minus VB. And I remember that you stick one vector at the tail of the other, because there's a minus sign, you switch directions. I did whatever, it's something like that. Okay, so that's the relative velocity. Now, before we continue, I want to point out what you're doing here. You're basically taking you can think of this vector in B like being an x-axis, and this vector for A as being a y-axis. Now, when you decide you want to look at relative velocity, it's essentially like rotating the frame. And so you're coming up with a new x and y, turning. So you think of me like this is x and this is y, or vice versa, or whatever. All I'm doing is I'm just turning it. I'm turning it because it just makes everything easier. Okay, so it looks like now my x is like this, and my y is like this. Perhaps this even looks more sensible, right? So, where of course, this was the velocity of A, and that's B, and now this is the relative, and here's my point. What is that? Right, now I ballyhooed last lecture on going from X, Y, and Z to net. The problem was we went from 3 dimensions to 1 dimensions, and you just can't just do that. You can't just say partial x, partial y, partial z is partial net velocity. You can't just do that. You have to do more analyses. So when you've got two vectors, and you're like, oh, but I only care about the relative, my point to you is you can't just consider the relative. You've rotated your frame in the x direction, but you can't forget the y direction at the same time because it's part of the analysis. Okay, so here's another way of saying that. 2 dimensions, 1 dimension, I need the other dimension. Where's my other dimension? Because I have to find that and then do my analyses. And so I know it sounds like, yeah, hopefully you get, if I'm going from description in x and y and I'm just turning things around, I still need to have an x and y, albeit new x and y, so I still need both of them. So that's the point. Okay, so I've already defined relative velocity as VA minus VB, that's pretty arbitrary. Okay, it turns out that the orthogonal, we also want this to be 90 degrees. It's really not that hard to figure out that what that is this thing we call it the center of mass. So again, this is 90 degrees to that. It's called the center of mass velocity. Okay, so there's my other, so this is my new x, there's my new y. And I have to continue the analyses with these 2 dimensions because I had started with 2 dimensions. Okay, next thing. Now that I have 2 dimensions, I'm going to write this down in a flow chart. A flow chart on how I get to average relative velocity. Now, again, in that chapter I sent you, I do this bloody step-by-step, no hand wavy, this or that. And so if you want to follow along with that, it's there for you. But I'm not going to do that in class because would take all day. It would just be pure algebra. It would take all day. So I don't want to do that. If you really want to know, it's there for you. You have that available. Okay, anyway. So let's go from 2 dimensions. Okay, we've got a Maxwell-Boltzmann factor. Sorry. Let me, before I do that, sorry, God. Before I do that, I want to go over what do we do with the Maxwell-Boltzmann to begin with, before I start manipulating. Sorry, I got a little ahead of myself. Okay, I've got A, I've got B. I've got a Maxwell-Boltzmann factor for A and a Maxwell-Boltzmann factor for B. And I distinguish them by just making one labeled with A and one labeled with B. But what do I do with them? To answer that question, let's say that we do some manipulation of a Maxwell-Boltzmann factor in terms of A. And the question is, to answer the question, what's the % probability of moving up? A lot of shorthand there, but I'm just got to do this kind of, I'm almost out of time. So we have these Maxwell-Boltzmann distribution factors. I showed you in the extra hour Friday that we can do things like, hey, what's the probability of gases moving up? And we did that. And you should know the answer even without any of this. What's the probability that in my gas chamber that a molecule A happens to be moving up versus down? 50%, right. Okay, so that would be 50%. Watch the video, if you look at the shorthand, you're like, what the hell is that? Okay, now, of course, we take Maxwell-Boltzmann of B, and by function, by the way, of course what I mean is that you're integrating over x, y, and z, but you're integrating the probability along z to only have a positive velocity. And of course, the probability that it is moving up is also 50%, because what the hell, what's the difference between A and B to begin with? Okay, what is the probability that A is moving up and B is moving up too? It's like two flips of a coin, it's what?
25.
Right. The probability of one is moving up is half, then the probability of the other guy, whichever one that is, you get to decide, is half, then that they're both moving up is 25%. So therefore, when you're manipulating joint probabilities, the way you do that is you multiply. You multiply them together, and then you go forth on your analysis. That is how you do this. All right. Okay, now I can go through a step-by-step flow chart. Now that we know what to do with Maxwell-Boltzmann Maxwell-Boltzmann distributions when we have more than one molecule, what we're doing is we're taking the product, and don't forget, the goal here is to manipulate these things to get average relative velocity. That is the goal. Now, of course, I'm going to have to include partials, because if I'm going to do some average of anything, I'm going to be integrating, so I better have some partials. Now, here's the trick. You can take those vectors up there and solve for VA as a function of relative velocity and the center of mass. Solve for the velocity of B as a function of relative velocity and the center of mass. So what you end up with are two new Maxwell-Boltzmann distributions. And I show you in the little chapter how to do that. So I show you how to do that. And don't forget your partials. And these will be in now relative velocity and center of mass. Okay, so that's step one. Again, that's why I don't want to do this in class. It's like 2 or 3 pages of algebra. Again, algebra is a 6th grade skill, but I swear to God, it's pages. Next step is you're going to integrate. You got the relative velocity, and the trick is you're going to integrate out, and you've got to remember that you're actually in 3 dimensions. So all that stuff we went through before, you run into it again when you do these other integrals. And again, they're done in the textbook I sent you. You see what you do? You're going to integrate all this. And again, look at the write-up. It just turns into a mess of constants. Let's call them Q. There you go. The last thing you do, you're basically done. You see, you've got your relative velocity, you get these mesa constants, you've got a Maxwell-Boltzmann as a function of relative velocity. This guy is still here, and all you would do is multiply it by and integrate it. And you know what? You're still going to have a Jacobian, a geometry factor. So I can't forget that. And relative velocities will still be net, so the lower limit is still 0. I don't know how you can have known that unless I tell you. When I ask you a question and it's probably not clear what the limits are, like in this case, I wouldn't presume that the limits would be 0, but I'm telling you that they are. What you end up with is square root of 8 kt over pi reduced mass, where reduced mass is going to be MA, MB. You probably have seen this in physics mechanics.
Over MA.
What was that?
Over MA plus MB.
Yeah, right, so reduce mass. You run into this when you're doing rotational, when you're doing some mechanic stuff, especially with rotation. Okay, so this is average relative velocity. Okay, so again, the textbook shows you how to do this for real. This is a very hand-wavy overview. It's not going to be on a test or anything because that would be impossible. Lastly, let me just show you one neat thing. All right, we're out of here, and we'll finish this up on Friday. What's cool is if you're talking about a homogeneous gas, in other words, the masses are the same, then a relative velocity is actually greater than the average velocity. So here's the point. You're writing a molecule in the chamber, and you're looking at those molecules, and you're saying how fast they're going. They appear to be moving faster because you're inside. And outside they appear to move slower. And I don't really understand that. I really ought to, but I really don't. I just know that this is what happens. And it's true. Okay, I'm not a little over. All right, homework session.